So now we want to talk about selectivity, which is a result of herbicide metabolism. So herbicide metabolism could result in selectivity. What do we mean by this? We mean chemical breakdown of herbicides in plants. So the speed at which these herbicides are broken down in the plants can result in selectivity. The speed at which these herbicides are destroyed within the plant. This can result in selectivity. There are basically three phases. Which involve herbicide breakdown, in plants. we have got phase 1, phase 2, and phase 3. All this lead to selectivity. What it means is that if the herbicide has been broken down, it ceases to be the herbicide. It becomes another molecule with different functions, and as a result, the plant is safe, is protected, because these chemicals no longer kill the plants. So let us look at what can happen in phase 1. Now, when I talk to students about herbicide changes which take place within the plants, I sometimes use an analogy or a situation which probably can make you remember what is actually happening. Normally, phase 1, I refer it to as it's like a hair salon where you have people going there to get, makeup and so forth. When they come up out of that salon or whatever, they look different, or they can become attractive. This is actually what happens to the herbicides. Of course, I don't expect you to say that herbicides are in the hair salon. What I'm emphasizing is that herbicides are undergoing some changes so that they can participate in other activities. So let us look at what is actually happening in the phase 1. Now, in phase 1, we have got an enzyme which is very important, known as cytochrome P450. Which facilitates chemical reactions that alter herbicides. the herbicides become less toxic after this. So let us look at the role of cytochrome P450. There's a basic reaction which is supported by phytochrome P450. NADPH plus this kind of reaction is an oxidation process which is catalyzed by cytochrome P450. Then we have to add our herbicide here. So if we put our herbicide here, what we are going to get is this NADP plus H2O plus ROH. This represents the herbicide. This is the altered herbicide. So once the herbicide has been reduced to the ROH, it's no longer the herbicide which we know. It's no longer active. So this is an oxidation process. And this is the key enzyme. So phase 1 processes number 1, we have got what is called oxidation. Number 2, we have got reduction. Number 3, I draw hydrolysis. Addition of water. Now on this one we've got under oxidation we've got I think about 5 processes. Here we've got 1 process, here we've got 2 processes, here we've got hydroxylation, or dealkylation. And dealkylation oxidative deamination sulfoxidation. So oxidation is 5 processes which we will talk about: hydroxylation, or dealkylation and dealkylation, oxidative deamination, and sulfoxidation. Then for this one, we've got nitro reduction. It's only one process. But for hydrolysis, we have got two processes. I think we have got amide hydrolysis and probably an ester. Hydrolysis. And you are saying cytochrome P450 is facilitating all these reactions. So all these reactions are facilitated by phytochrome P450 in phase 1. So let us go to the slides and see the details of these reactions. So herbicide metabolism. Herbicides are degraded very fast in tolerant plants. Herbicide degradation is slow in susceptible plants, effect on herbicide concentration at the site of action will determine whether the plant is going to die or not. Okay, let me so herbicides can be degraded in phases. We have got oxidation, hydrolysis, and reduction on the top part. This can be facilitated by cytochrome P450. Then we have got conjugation, which we will talk about later on. But we want to focus on phase 1 first. As I've indicated, there are 3 phases: oxidation, reduction, and hydrolysis. That is the phase 1 reactions. But as I indicated earlier on, it could be many things. 5 things under oxidation, 1 reaction under reduction, and 2 processes under hydrolysis. Phase 2 reactions, we've got conjugation. Then phase 3 reactions, also conjugation reactions. Here we've got conjugates moved to vacuoles and incorporation into cerols. I'm going to just focus on phase 1 before we break. The phase 1 reactions involve cytochrome P450 monooxygenase, or just cytochrome P450, which occurs in the endoplasmic reticulum. Sometimes we call it the mixed function oxidases, but just remembering cytochrome P450 is enough. Now, oxygen is incorporated into the herbicide molecule. This is the mechanism in which it alters the herbicides. The oxygen atom is converted into water by an electron donor, which is NADPH. So this is the equation which I tried to explain earlier on, which is catalyzed by cytochrome P450. Those in red, these are the ingredients which are required for this reaction. RH represents the herbicide. So it will need oxygen, hydrogen, and NADPH, and the cytochrome P450. It's not only herbicides which are changed within the plant systems, but any foreign body, and we refer these as xenobiotics, and we are not going to talk more about those things. Now, all the herbicides have one or more of these functional groups: the OH, NH2SH, COOH, CN, OCH3, CH3, and SCH3. These are the functional groups which may be added to herbicide molecules by cytochrome P450 activity, leading to the reduction of phytotoxicity. Remember, I said that I always refer the phase 1 as some kind of a saloon or something, where you have a beautician or cytochrome P450 making changes to these molecules so that they can participate in further reactions, like these ones. Okay, so what are the oxidation reactions? Hydroxylation, any dealkylation or dealkylation, oxidative deamination, sulfoxidation, or thioether oxidation. Now, under hydroxylation, you either have what is known as the benzene ring, which is the first line there with Cl. Hydroxylation means changing the Cl, which is chlorine atom, to the OH group. Or you can have an aliphatic group, which is represented by the example on the bottom there, where you have a chlorine atom attached to R. R is a complex group of things, and it can be changed to ROH. Once you have an OH added, then the herbicide is no longer a herbicide as we know it. Here again, we are just giving examples, like this can occur in Basagran, where OH can be added to the Basagran molecule. Then it no longer functions like a herbicide. If you focus on the bottom, where we have put an OH to Basagran during hydroxylation, and this can take place in soybeans. In dealkylation, you need that component R, which is joined to NHCH3. That component can be removed during N-dealkylation, and you remain with RNH2. And this can happen to atrazine, where you have on top there, where you have on the left, top left, where you have an N attached to CH2 H5. A simplified version is on the bottom in red, where you can change it to NH2. Or dealkylation, the R is the bigger part of the molecule, but we have got an oxygen instead of nitrogen now attached to that group. In this case, if you remove the CH3, that is O dealkylation, you remain with the ROH. And this can happen to 2,4-acid, which is the herbicide. And that arrow in red is indicating where the breakdown can take place. sulfoxidation or thioether oxidation, the thing to remember is that you should have an S in alpha, you should have a sulfur bond. So you have got RSCH3, the sulfur there will get attached to the oxygen shown in red. And this is the sulfoxidation or thioether oxidation. It will change the activity of the herbicide. Here's an example of the herbicide with the sulfur prometrine. You can see where the sulfur oxygen has been added, and this herbicide ceases to be the herbicide which we know, and the process is known as sulfoxidation or thioether oxidation. Here again we've got a big molecule of EPTC, but you don't need to remember all of this. Just spot where there is S in the molecule. That is where the oxygen is going to be added. And we simply call this process sulfoxidation or thioether oxidation. In fact, if you are given any molecule, if you spot S, sorry. Hello. 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 Yeah, ndine lecture at the moment. And ndiri kuticha. Ndimabasa, I'm teaching students right now. Okay, sorry for the disturbance. So if you spot an S, you know that sulfoxidation is likely to happen. Now, there are cases where you have two nitrogen atoms connected together, like in this one. Where you have R, NH, then NH2. This can be converted to NH2 in red. It's known as the oxidative deamination. The thing to remember is that there should be two nitrogen atoms joined together in any part of the molecule. Then you are sure you are going to get deamination, oxidative deamination. This can happen to metribuzin, where I've shown in red. That is the position where you can get two nitrogen atoms. If you look closely at the structure, you can see where oxidative deamination is likely to take place. Again, if you look at that molecule, you see there's an S, so there's also a potential for sulfoxidation. Reduction is just one process. If you have an NR joined to NO2 or nitrate, it can be converted to an ammonium through reduction, and it's just one process, reduction. Here we've got trifluorine, a complicated molecule where we have got NO2. It's a potential area for reduction which can be converted to NH2. The rest of the molecule doesn't matter. Hydrolysis, the reaction of the herbicide with water. Here you have an ester or amide groups which participate in this reaction. It could be nitrile or amide. So this is the structure of an ester. You've got two R's there. Then in between you've got the carbon C attached to oxygen. Then to another oxygen with a double bond. This can split into an acid and an alcohol, indicated in red. Ester hydrolysis. Again supported by cytochrome P450. Here we've got the actual molecule 2,4-D methyl ester. We can spot there in red where the split is likely to take place, where there's an ester bond. And this is an example of de-esterification which can take place within the plant to release the acid, the 2,4-D acid. Then we have the amide hydrolysis. What is important is to remember the structure of the amide. Remember what is inside those two R's, NHC then the oxygen with the double bond. Again, amide hydrolysis shown in red on the propanil. Here we have got the cyano group, which is a triple bond between carbon and nitrogen. Now, with the nitrile hydrolysis, you can convert the triple bond to an amide, then to an amine, and also to an acid. Like here on cyanazine bladex, where we have put red circles, cyano group. Firstly, it is converted to an amide, then a carboxylic acid. Probably the amine part is lost as ammonia in the process. Again, bromoxynil with that triple bond cyano group can be converted to the acid, but the amine bit probably is lost as ammonia, like what is indicated, plus ammonia. Probably I will stop here.
Okay, thank you.